Great. So I have the unenvious position here of teaching quantum computing in 15 minutes between beer and pizza. So it's good for digestion, I think. First, I got to teach quantum physics and then the computation. Let's not do that. Today, I'd rather talk about what it can do, because it will take literally hours, maybe days, maybe 7 years of a PhD to teach you really what quantum does. And in some ways, it's irrelevant. We know how to use this stuff, and that's what's important for you to take away. It's really cool how it works, but that's really not the point. Many of you don't really know how your iPhones work, down to the OR gates and the AND gates and all the things that go on the semiconductors that are in there, and you probably don't think about it a lot. And eventually, we'll be thinking that way about quantum computers, I hope. But basically, the computers we have today, all of them, are based on these mechanical device things. And which one of these is a laser? None of them. Okay. Or top one? No, maybe not. I'll just have to point. Old tech. Here we go. So I guess we could go back to the 1830s with mechanical devices that did computation, but actually more accurately, we could go thousands of years back, and every civilization had something like an abacus, because our brains lose track of counting at some point. Okay, so that's where the whole idea of let's have a computer came from. They're counting devices, they've been counting devices, and they're all classical counting devices. They have things that move. And later on, we had the Turing device during World War II, which is also literally a physical device that you could crank, but it did computation. And that found the U-boats and won World War II for the Allies. And then later, they turned the cranking machines into these things called vacuum tubes, and you might have seen the ENIAC computer, the first electromagnetic computer since the 1940s, but it's basically the same thing as this, but electrified. On-off switches. Now the on-off switches are electrical instead of mechanical, okay? And then we moved on to this wonderful thing called the transistor, and that's what our computers are made of now. We just have lots of these, but they're also basically on-off switches. They're electromagnetic on-off switches. And every single computer you see out there, from the smallest little pocket calculator to your iPhone to your supercomputers, including the IBM Summit supercomputer, the fastest one in the world in Oak Ridge right now, are made of these on-off switches. Okay, for the first time in human history now, we have computers that work differently. And they work differently because they're quantum. They're not on-off. Some people say incorrectly that they're both on and off at the same time. That's not really the right way to say it in physics, but basically in physics, when things get really small, they get really weird, okay? And that's enough to know. They get really, really weird. And so this atom in my fingernail is here, but it's also on the other side of Andromeda right now. It's less there, a lot less there, thankfully, than it is here, but it's actually there. Also, now. And Andromeda is also here now. It's just less here than it is there, okay? But when I look at Andromeda, it's there. How's that? All right? So that's just how it works. So it's on and it's off, or it's neither or both, whatever way you want to look at things. But when I look at it, it's either on or off. And so we're able to use that to do some pretty amazing things. Because now, instead of having just on or off, if I have 3 bits, I have on or off, on or off, on or off. So it's only 3. And combinatorially, it's a lot, but you can only have one bit stream that's 3 things at any one time. You can't have both. With the quantum, we can actually have both. And we can entangle them together. It gets even weirder, right? Because when things get small, they become the same thing to each other. And so, coins, when you flip them, they're kind of independent. That's how we perceive things, right? But small things interact with each other. So if I get a heads here, that one has to be a tails. And that one's tails, that one has to be heads. They get correlated, which is weird, because we don't see things like that in our daily lives. But the great news is, anyway, we can talk about how all that works and whatever. It's either God or multiple universes, as same physicists would like to tell us. Really, that's their best guess, is that it's multiple universes, just like the Star Trek episode that does this. But the good news is we can use it, we can control it, and we can actually do some cool stuff with it. And that's what's important to take away from this. So Quantum started in the 1920s. We got this idea that things can be here and there, and you may have heard Einstein say, well, God doesn't play dice, meaning that things can't be here and there at the same time. That just doesn't work that way. It's either here or there. We want to have causality. We like nice, clean, causative solutions in our lives. If I go here, I want to be going there and not there and here at the same time. But that's not how the world really works. We figured that out in the 1920s, 1930s. There was still some argument about whether that could be the case during Einstein's time, but by the time 1930, 1940 came around, 1950, Einstein says, well, it's the biggest mistake I ever made. I was wrong. And the world actually is that way. God does throw dice. My fingernail is here and on the other side of Andromeda at the same time. And we can prove it mathematically. And not only that, but we can actually learn to control this thing and use this thing and interpret this thing. And now, through the years, we've figured out exactly how it works mathematically. But importantly, in the 2000s, we learned how to actually use this stuff, to actually use it to do something, and to control it in a way that we can quantify and all of this. And we were able to come up with 1 qubit, quantum bit, one on and off at the same time thing that when I look at it becomes either a 1 or a 0. And then we were able to, in the 2010s, end up with multiple of these things in a machine and have them actually work with each other to do actually a useful calculation. It was still a toy calculation, something you could do better on a pocket calculator, but we could use this mechanism now to actually do something and prove that we could do something. And then in around 2016 to 2018, around that time frame, we actually started having real hardware getting really close to doing something better than even a classical computer can do based on these mathematics and the power of the mathematics that we can garner from this new mechanism. So you may have heard of the Google quantum machine, the IBM quantum machines that are out there, and actually you can go play with them today. You can actually touch a quantum computer, well, not physically, but over the cloud. You can interact with an actual quantum computer online today. It's free. Go to IBM Q Experience, and you can use a 5-qubit machine and do some pretty cool stuff. And then in 2019, at the end of last year, John Martinez and his team proved pretty definitively in a big paper that a quantum computer with 53 of these qubits, quantum bits, could do a calculation that would take a long time for a classical computer. Now, there was some argument after that whether what you did in 3 minutes in that experiment, they said in the paper it would take 10,000 years on the Summit supercomputer based on their calculations, but some clever people at IBM said, well, if you did this and that and the other thing, it would take 3 days. Only 3 days, okay? Only 3 days on Summit supercomputer. Summit supercomputer, okay, just so you got to understand the relevance of this, runs on 30 megawatt hours, okay? That's enough to enough electricity for 7,000 homes, okay, per hour, okay? The quantum computers that I'll tell you about, the one that Google uses, is about 30 kilowatt hours. It's 1,000 times less energy. And it took 3 days to do something on that quantum classical computer that took 3 minutes to do on the quantum computer. And actually, the other one was just theory. When they did experiments, it looked more like 10,000 years. Okay? So, yeah, the numbers are starting to get pretty crazy, right? So this is because of the thing of 2 to the n. So when I have 1 qubit or 2 qubits, it's really powerful. And I don't need a lot of energy. This is actually what a quantum computer looks like. The actual quantum computer itself is down here. It's a little chip, and I can put 1, 2, 53, 100 qubits, 1,000 qubits, and probably about 10,000 qubits on that one chip. Nothing else changes really except for the wiring, okay? And the energy output of that thing is still 30 kilowatts. And it's all refrigeration to get this thing down to about 10 millikelvin, which is much, much colder than deep space. So we use a special kind of helium to do that. But that's the quantum computer there. And even when we have lots of these things, the energy that you need to do anything doesn't really change. So that's significant because you have 1 qubit, you double the amount of computational power, okay? Because it's both 1 and 0 at the same time, that means 2 to the n. N is the number of qubits you have. So every time you add 1, okay, you double the computational power. Why is that important? Well, why is computation important? Well, for chemistry, for things that are quantum, it's really, really hard because chemicals are also like here and there at the same time. You may have heard like this atom can be here and there and you can't know where it is at any point. But we can calculate it if we had enough computational power. Water, the energy of water is perfectly calculatable on this, okay? You get up to methane though, and you need something like that, okay? You have 4 of those things together about, or 4 or 5 of those. It takes a week on Summit supercomputer to calculate the energy exactly. It's exponential. So for exponential problems like chemistry, this becomes really relevant. We know exactly every equation for every chemical reaction in the world, and we've known it since the 1920s, 1930s. We know exactly what's going to happen. We should know mathematically what's going to happen when I combine this and this before we do it without any experimentation. But we don't have the computational power to calculate it, so we're forced to do alchemy and mix this with that and see what happens, see what blows up and what doesn't. And we're still doing that because we don't have enough computing power. But if we have a computer that's exponential, the world starts to change. So to give you an example of what this power looks like, on a classical computer, if you want to beat 2048-bit encryption, well, everyone says that's impossible. Well, it's not technically impossible, okay? If you had enough supercomputing power, you could solve that problem with a classical computer. Problem is, to break that number, with the best classical algorithm, it takes 10 to the 34 steps and 317 trillion with a T years. Okay, so if you got an extra 317 trillion years in a Summit supercomputer, you can do it. You can break every single encryption key out there, okay? That's why people say it's impossible. It's not. Now, if you had the Tesla of quantum computers, which we don't have now, we're kind of at Model T or maybe bicycle right now, okay? But when we have that Tesla, we know mathematically when we have that Tesla with a few million of these qubits, the logical qubits that we may need, we know mathematically we can prove, and it's been proven, it was proven in 1994 by Peter Shor, the guy who created this algorithm. De facto, mathematically, no questions about it. We can do it in 10 to the 9 steps, and our current estimates is that would take about 8 hours. 317 trillion years in 8 hours, okay? Maybe 8 hours, maybe 2 days, maybe, our estimates might be wrong, but it's kind of in that category, okay? But it doesn't matter. Even if it were 1,000 years, it'd still be a serious difference from 317 trillion years. Okay? Impossible to possible. So when we're talking about quantum computers and why this is so cool, we're not talking about a better supercomputer. A little bit better, really better, like mucho better, super, super better. This is something that it's hard to even fit in your head, okay? Even mathematically hard to understand. Give you some more kind of numbers to gauge this for you. 30-bit qubit error-corrected quantum computer would be more powerful than the largest supercomputers out there today. That's only 30 qubits. Google now has Sycamore on that Supremacy thing. They have right now 53, kind of imperfect, but 53 qubits working. And 100 to 200 qubits will equal to the power of all of the computers on Earth, every cell phone, every calculator, every supercomputer on Earth. It's actually, when you get to 2 to the 150th, it's equal to the number of silicon atoms on Earth, okay? So it's greater than that. So there's not even enough silicon atoms to build that many computers to even keep up with this. So what gets more important and more interesting, I think, here is how can we use this kind of power. Oh, and when you get to 300 qubits, 2 to the 300th is more bits than there are visible atoms in the visible universe, okay? Pretty mind-blowing stuff, all right? This is revolutionary. So when I say, this is revolutionary, every CEO gets up on the stage, I bet, says, our technology is going to revolutionize the world. We have the best anime dating app ever. It's a revolution. No, this is the real thing. It really is. So yeah, hold on to your seatbelts. We beat anime dating apps every day of the week here. Not that those aren't useful. So people are getting involved in this because it's exciting. So we have a bunch of corporates that you may see in the news working on these machines. They're real now. You can play with them. We play with them every day. We play with actually the super secret in the back of the room ones. Honeywell's in this, Google, IBM, Intel, Alibaba Group, Hitachi Fujitsu in Japan, Microsoft, AWS, Atos, Toshiba. But we have some problems because they're all different. Just like in the early days of computers, we didn't know if we were going to use gallium arsenide or silicon or this or that, the vacuum tubes or transistors. Transistors eventually won, but right now we don't know what's going to win. Is it ion traps or superconductors or this? So there's a lot of frameworking compatibility problems there. Deployment on computing resources is a problem. Data management for doing the experiments on this is very different and complex. And the reproducibility of your experiments on these things is really important when we're in this development stage. We've developed some of these tools for workflow management so that we can actually experiment and know what is IBM versus what is Rigetti, what's the difference between these 10 qubits and those 10 qubits and how they behave. So why is this a problem? So why do we have a software company to do this? Well, to do computation on a quantum computer, it's not just the quantum computer you use, because the quantum computer is like this flaky thing that's 0 and 1 at the same time. Eventually you have to turn that into numbers and look at it on a screen and do something with it and analyze it, and then send back your next query to the quantum computer and iterate. So a lot of computing happens actually on a classical computer. And so you update your parameters on your classical computer, you send it to the quantum hardware, and it comes back. Looks really simple, right? But that chemistry, water, energy problem that you saw that I put up there looks more like this, okay? So it's complex. There are a lot of things you got to do on the classical computer before you even do, that's your quantum computer thing. That's 100 lines of code. That's millions of lines of code, okay? But that does some really powerful stuff, okay? So it's worth doing all this to do that, but you got to manage all that. So we need software companies, and we've built some markup language capabilities to write these workflows. So here we create a molecule, we run Hartree-Fock on our classical computer, transform our Hamiltonian, do all these steps, and then we can send things out to the quantum computer here and do the quantum calculation and then come back to the classical calculator. And so what does that look like? Here's what we can do. We can basically program our workflow that we're going to do this, this, and this, and then what we're going to send to the computer. We choose which quantum computer we're going to use, Rigetti's, IBM's, such and such. Here we're going to use Rigetti's simulator. And then the coolness of this is now I can run this. Here I'm running on a simulator, and I'm changing 2 lines of code here to IBM Q to run it on IBM's actual quantum computer here. So you're seeing an actual run on a real quantum computer today. There. Actually, one of their bigger ones. And we can compare the results. We send them out. We collate them back, and then we can graph it and look at this stuff. So it's pretty amazing what we can do. So with a little bit of software ingenuity here. Google Supremacy announcement again: 200 seconds versus 10,000 years. 53 qubits. Sycamore had solved this random circuit sampling problem in just 200 seconds. They've done it. So what does this mean? It means that an airplane has flown. We're in 1903, okay? We're actually 1904 because they did it last year. So that's a big difference, right? We've already gone along. And as you know, technology is getting faster and faster and accelerating. So why is that significant? Because if you use that as an analogy, you could say, and you'll hear pundits out there saying, well, it's not really an airplane. It only flew 600 meters, which is true. It only flew 600 meters. It didn't go over a mountain, didn't cross the ocean, really couldn't fly much more than one person, and it was kind of semi-controlled. It kind of sucked. It wasn't really an airplane, but it was. And based on that, we knew one thing that an airplane can be. And that's what we know from the Google experiment. There's no question out there that the airplane is flown. Now, are we investing too soon, or are we investing too much? And you can, be on both sides of that equation, and you can be a pundit for or a pundit against. But to take that analogy back and go to 1918, and you're in World War I, and you don't have an Air Force. Maybe not the best analogy to use, but I think relevant to think about this. And these things are going to be important for all kinds of reasons, including dual use reasons, national security, the safety of our social security numbers and our data and our infrastructure and everything can be cracked by this kind of thing. And all of these advantages we can get in chemistry, in materials, in all of these kind of areas, it's important. This is a significant milestone in humanity right here. And it's important for us to know that. You know, right now we're in these noisy computers, but we're eventually going to get to a point where we have fault-tolerant computers that can do much more, the Tesla of these types of computers. And when we get there, we'll be able to do things in optimization. Think about saving carbon by optimizing the truck routes that we have in this country right now. We don't do any of that. You might think FedEx has a big computer algorithm that, you know, determines where a package is going to go. No, it's a person with a clipboard saying, I think we can get one more pallet in that truck. That's literally how it's happening. And there are simple business rules that they run on Excel spreadsheets in their little departments to do it. Because it's too hard computationally. And I can get into the math of that, but it really is too hard. Machine learning is going to get much better. Yeah, we can now use it to separate things out into 2 groups or 3 groups or 4 groups. But what if you have 36 types of cancer and 500 different biomarkers? How do you draw a line through those data points? You need high dimensionality, and that's what quantum computers can do. Simulation and modeling, quantum for simulation of financial markets, all kinds of things like that. Right now, we're limited by the computational power and our productivity on these kinds of things, and that is about to change. So where is this going to have global impact? Just about every area of human activity. If you think computers have affected all of our areas of human activity in the decades that we've had it, here we go again, but at an exponential level. And I know that sounds like hyperbole, it is, but this is hyperbolic technology. By definition, mathematically it is. So you really need to start thinking about what the uses are going to be. I don't have all of those answers yet. People in this room, people around the world have to start thinking about what the positive and negative uses of this could be and prepare for it. Psychologically, technologically, ethically, what do we do? Because the world's about to change really significantly with this. Environment, human health, energy, food security, defense and security, just about everything. Thank you.
Awesome. Wow, Christopher, what a way to end the night. Thank you so much for that fantastic presentation. I'm sure there's plenty of questions, but quick one from me to start. Is the quantum world, in terms of the folks that are working on this, relatively open? It sounds like they're relatively open to sharing learnings, to try to move the entire field forward. Is that an accurate assessment?
Yeah, we publish a lot. Most of the scientists do. Put out a paper on what they did. They released all their data and even their architecture of their computer to the world. We're really in this kind of pre-competitive, we're competitive with each other, but a kind of a pre-competitive environment where all boats rise. And there's a lot of interplay and cross-fertilization across companies. Our company exists to create a platform that you just saw that lets us run Rigetti and IBM and these things and allow different researchers to try all these different things on a common platform.
Awesome. And one more from me. The first customers for this, I know you touched briefly on it, but just elaborate a little bit more on like the first folks that would be on Zapata.
Sure. We know for sure that chemistry, materials, pharmaceuticals, anything that deals with chemistry is going to be majorly impacted. So those companies are early adopters. They know their world is about to change completely. So they're kind of in the front line. Even this may take 5 years. 5 years to them on their time frame when this is going to completely disrupt their industry is nothing. Financial companies also right here in New York City and Wall Street are getting very much involved because this will affect how they can predict things and predict markets much better than they can now. And then anyone in logistics, optimization, that can be across industries. It's not really a vertical. All companies have optimization problems. And that's where another area.
Awesome. Thank you very much. One from the front.
Is it premature to think or talk about software that's actually running on the quantum computer? For the time being, is the action going to be on the classical computers and then just running the calculations on the quantum computer? or will there be a whole ecosystem of software that kind of runs literally on the quantum computer?
Yeah. Well, a piece of it's going to run on the quantum computer. What you just saw, actually, that IBM one on the bottom was running on a quantum computer. You'll never get rid of having a classical computer because even the quantum computers themselves use classical electronics to do what they do, to send signals down into quantum land and come back. And when it comes back, it becomes a 1 and a 0. So what do? How do you visualize that? You're not going to visualize it on a quantum computer hovering between 1 and 0. You eventually, so there's always going to be a role for classical computation in this whole cycle of things. So when we write a quantum program, we're actually writing a solution, a workflow like you saw that runs partially on a quantum computer and partially on a classical computer, and that won't change.
Is there an operating system for the quantum computer that's going to evolve the Microsoft?
Mind repeating the question?
We hope we become the Microsoft.
Yeah, we got one back here.
I had a question about scaling, because I don't imagine everyone can have like a helium freezer in their pocket for their quantum computer. And then also with privacy, because you can break a 2048-bit encryption in 8 hours, is that all the bandwidth on that one single encryption, or can they do multiple encryptions at the same time?
So yeah, that's one single encryption there as far as the calculation goes. We're nowhere near breaking that yet, just so you know, so don't go out and change your social security number or anything today because of it. But keep in mind that if that's 10 years away, people can save the data and wait 10 years. And there are some national entities that may be doing that. And then the scaling issue, we can cover that probably in the next session.
Thank you very much. Very enthusiastic presentation. I just wanted to ask you, you know that in binary 1 plus 1 is 1 0. But in quantum computing, it's not always 1 0. It might be 1 0 with some probability. So, and it depends on the computer. That probability problems, chemistry, what you said, it may be solved by this method, but not our usual algebra problems.
No, this
probably.
works. This actually works on linear algebra.
Yet.
At the end of the day, it is based on statistics.
Yeah. So what that's the like statement. My question is about your software. Can your software regulate this probability dependently on the computer which you use, or you just get a result which the computer gives without accounting for real probability connected to this calculation?
It's statistical, but it's not random. Well, it is random, but it's not. Okay? At the end of the day, these things become binary numbers. So the physics doesn't really work that way. It's not ambiguous. We know. No, the algorithms can do discrete math, actually. That is actually a discrete math problem, Shor's algorithm that we're using there. It's not a heuristic. And the way it works is using interference and a bunch of other things mathematically that I can explain to you on a chalkboard. But we can use these quantum computers to do discrete mathematics. It's not just random. We end up with an answer.
Thanks for your presentation. Do your energy savings calculations take into account the cooling requirements for the hardware?
Yeah.
And second,
yeah, that is the cooling. All of the energy on that fridge, the dilution refrigerator, we call them DIL fridges, is 30 kilowatt hours.
nice. And is Google insurmountably ahead, or how do you catch or surpass Google at this point through a different methodology?
Well, Google has 53, but you saw IBM has in the 50s now as well. They may have a little bit lower noise levels from what we've seen, arguably than IBM, but they're both kind of neck and neck. And the ions are coming on really fast, so it's really hard to pick a horse right now, honestly. And that's what makes it so exciting. That's what makes it so exciting to get in on the hardware side. There are other ones I didn't mention, like photonic methods of doing the same thing. There are a lot of ways of getting this 1 and 0 superposition type of thing happening.
What is the biggest bottleneck in quantum computing? Do you think we need like an Intel of quantum computing or like a Bell's Lab that actually creates the software for PCs? Like, what would you call the biggest bottleneck in quantum computing?
The biggest, I'm sorry.
Bottleneck.
The bottleneck, well, the bottleneck is the fragility of these quantum states. Any kind of noise The little noise gremlin, the little noise monster destroys things. So getting a qubit and a qubit to interact is really important. We call it entanglement. So we need this qubit to interact with this qubit and get that correlation for this calculation to work. The problem is we need them to interact, but not interact with the environment because then they lose their quantumness. So simultaneously, it's a tightrope walk, right? We want them to interact with each other, but not with the rest of the universe. And that's a really hard thing to do. We don't want them to crosstalk with the wrong qubit either. So controlling that noise really is a bottleneck now. It's a really hard engineering thing, but we know what it is. We know what the noise sources are for the most part, and we know kind of how to mitigate them. We're coming up with better and better engineering to do it.
So I work in banking security, and I'm already aware that anything we put out on the web today has to be quantum secure, as we say, because someone is sniffing it and saving it, and you just can't ignore this technology. But where I'm thinking about is the impact on things like chemistry, things like battery technology. I mean, if we can just get like a tenfold improvement in batteries, our civilization is profoundly different.
Absolutely.
Is that going to happen?
Absolutely. It's not an if anymore. The airplane's flown. It's a when. Now, is that when? I'm not here to predict. Is that 20 years? Do we need a fault-tolerant computer to do some of those things? Possibly. Can we use something in between now and that Tesla fault-tolerant computer to do something useful that gets us along that way? Yes. How much? I don't know. But that's kind of the exciting part of being in the field now. We really didn't know what all the useful applications of the ENIAC or vacuum tube computing was going to be, but we ended up getting IBM, and then people came up with, well, you can play games. And nobody had imagined that. And I don't want to, disparage the technology by saying that. Actually, it's an exciting thing. We don't know what the uses could be, when they're going to be, but yes, things like chemistry, things like this are going to be affected by it pretty incredibly. And it's even smaller things. Blockchain right now, I think that I heard that just mining coins takes up the entire energy of a country the size of Estonia every year, and it's growing. That is more than that now. And it's sick. It's really sick that we're doing that. But what's the solution? The solution is to get better computing powers. I don't think blockchain is going to go away. There are many reasons that it's there and that it exists, even aside from Bitcoin. But we need to do a better job of that, and there's the solution here. So someone is going to think of a way to do those kind of calculations in Bitcoin creation using a more ecologically sound technology.
Christopher, that is all the time we have. Thank you so much for coming and presenting at Hardwired.